Welcome back to Physics 221. This is chapter 34, ray optics. So we've already had a chapter on wave optics where we learned the wave theory of light. This chapter is about the ray theory of light. So you can think of light as made up of particles. So here's the objectives: to understand the ray model of light in its domain of applicability, to understand reflection and refraction, to apply ray tracing from situations ranging from apertures to image formation. We'll be doing a lot of drawings. It's probably best if you have some graph paper. To understand how, when, and why images are seen, to recognize that diffraction limits the resolution of optical systems. We already did that. I think that's wrong. It should say, all right, so basically, a lot of what we're going to be doing is we're going to be, like somebody's going to, let's just say the problem gives us a certain lens with a certain focal length. And then they say that the object is located at a certain distance. We have to find where the image is located. So we're going to do it in two ways. First, we're going to learn how to do it graphically. So we're going to draw a lot of pictures with a ruler or a meter stick. And after we get all familiar with that, we're going to do it mathematically. Now, we're actually going to do lenses as well as mirrors. So when we go through and do all the diagrams, you want to save those, because every example we do with the diagrams, we're going to do again, we'll repeat with the mathematics. Now, make sure you read the textbook, especially the beginning sections. There's a lot of background conceptual material. I'm not going to discuss much of that in class. But if you don't understand it, I mean, what I talk about in class is not going to make a whole lot of sense. So make sure you read the book. Okay. So we discussed this in the last chapter. The question was, when do we use the wave model of light? When do we use the ray model of light? And hopefully you'll remember we had a piece of paper here with a hole in it. Then we had the screen. And we had a light source. And what we said is that the light goes through the hole here, and if it doesn't spread out, that means that light is acting like a ray or like particles. So we'll use the particle model. If light spreads out, so the image is much larger, or just let's say larger than this, then we're going to use the wave theory of light. So here, so this was for just laboratory experiments. When light passes through openings less than about 1 millimeter in size, diffraction effects are important, so we have to use the wave model. When light passes through openings greater than about 1 millimeter in size, diffraction effects are usually not important, so we'll use the ray model of light. So that's where we are. So here's the ray model of light. It's not very complicated. Number one, light travels in a straight line. So again, think of a laser pointer. Think of you shining a laser pointer out at night or something like that. Number two, light rays can cross, right? They don't interact at all, right? They just go through each other, you know? Light rays can travel forever unless they interact with matter. Now there's 4 ways light rays interact with matter. So this is material 1, here's a boundary. Here's material 2. So one way is reflection. So the light ray comes in and it reflects. Another way is refraction. And we'll talk about this in gory detail. Another way is refraction. It comes in here and then it bends. I talked about that before. You're sitting on the edge of a pool. Here's water. You look at your leg in the water and it looks like it's bent. That's refraction. There's scattering. The light can scatter off something, or it can be absorbed. All right? Okay. Let's see. Any object is a source of light. Any object is a source of light rays. I mean, why do you see me now? Because the light from the ceiling lights are reflecting off of me into your eyes, if you were here. So any object is a source of light rays. And what does the eye do? The eye, this is a human eye, the eye focuses these diverging lenses. Okay? So that's how we see. So here's a question for you. So I want you to just imagine this thing is really, really long, okay? Really, really long. So a long, thin light bulb, like a fluorescent light bulb, illuminates a vertical aperture. So this is a slit, which is located a short distance away. Which pattern of light do you see on a viewing screen, which is behind the aperture? All right, so pause your video and figure it out. All right, we're back. So that's the answer. I hope that makes sense. Let me kind of see if I can draw it. So, there's just pretend that's a slit. This is the long light bulb. And here's the screen. Let's say here's the screen. Well, you know, the light from here is going to go over here. Light from here is going to go over here. Light from here is going to go here, you know. And then, all right, so that explains why it's this way. Then, of course, it's going to go here, here, here. So it's going to, where is it? Cover the whole, pretty much the whole screen. All right. Let's talk about reflection. Reflection. So, and you know, this is just an idealization, right? I mean, you know, there's no such thing as a perfectly flat surface. But for all intents and purposes, we're going to consider this a perfectly flat reflective surface. So, here you have an incoming ray, here's outgoing ray. What do you notice? You notice that this angle, which is called the angle of incidence, equals this angle, which is the angle of reflection. Now, so that's the rule. I mean, there's really nothing to say much except for that. Okay? So theta incident equals theta reflection. Now, here's something you have to understand. Whenever we talk about these angles, we also talk about the angles relative to this normal. Yeah? So here's the surface, here's the normal. This is the angle we're talking about. These are the angles we're talking about. We're not talking about this and this. I mean, obviously, this is equal to this. That's true, but I don't care. Right? And you'll see later on, we're always going to talk about the angles relative to this normal. All right? So there you go. That's the law of reflection. Theta incident equals theta reflected. That's it. Isn't that great? Not so bad. Let's talk about a plane mirror, like you might have in your, you know, I don't know, in your apartment or something like that. So here's the mirror, the plane mirror. So it's flat, right? And this is some object. This is you. And so, you know, the light is reflecting off of this, hits the mirror, and then it reflects back in your eye. All right? So that's kind of how it is. So, what do you notice? Well, first of all, when you're looking at the mirror, the light is coming in this direction towards you. So you're actually thinking that the image is over here. Now, it's not, right? The object is here, correct? It's just that the light reflects. But again, you know, the way that we think about it, the light is coming from this direction. So we're going to say this is a virtual image. Why is it virtual? Because this is not real light, right? We're just backtracking on these rays of light here. All right? So a plane mirror will always have a virtual image. So we think that the image is located behind the mirror. All right? Okay, so that's number one. Virtual image. Plane mirrors always have virtual images. Okay, what else do you notice? Hopefully you'll notice that this distance is that distance. Okay? So this is called the object distance, S. This is called the image distance, S prime. So S equals S prime. What else do you notice? So you can make a line from the object to the virtual image, and you can see that as perpendicular to the mirror, right? There's a right angle. So that's really all there is to it. It's for a plane mirror. All right, always virtual image. This distance equals that distance, and line is perpendicular to the mirror. All right, next, let's talk about refraction. There's a nice picture, right? This is an ordinary pencil, but it looks like it's bent. It's not bent, but that's what it looks like. So, and we've all seen that. So here's the picture. So here's air, and here's water. In air, we're just going to say that the index of refraction is 1. Water, the index of refraction is 1.33. So here's your incident ray, and what do you notice when it hits the water? It bends. In fact, and this one bends toward the normal, right? So here you go. Comes in, doesn't go straight, bends toward the normal. But hey, but some of that light is reflected, right? So we still have this angle equals that angle. That's why it says theta 1, theta 1. But obviously theta 2 here is less than theta 1. Okay, so when you go, here's why, well, when you go from small n to larger n, the refracted ray bends toward the normal. Okay, great. Now, let's do it the other way. Now let's say that the light source is coming from in the water. So again, some of that light is reflected. So this angle equals that angle, no kidding. But some of it gets through, and it's bent. But what do you notice? What do you notice now? This one, come on. This one, the refracted ray bends away from the normal. So here, it refracted toward the normal. Here, it refracted away from the normal. So, how do you explain that? You explain that with something called Snell's law. So Snell's law just says n1 sine theta 1 equals n2 sine theta 2. There, you got it? That's all there is to it. Now, there's one little thing you got to be aware of. So there's a convention or an agreement. So we always use n1 to be the incident side, or n1, theta 1, whatever one, right? To refer to the incident. And theta 2 or n2 is always the other one, all right? Okay? So the outgoing, yeah, that's, okay, the outgoing. So here, look at, so here we're starting from the air, so we label this n1, theta 1, theta 1. Then it goes, we don't care about reflected, right? All we're talking about is refracted. So here's the outgoing ray, so that's n2 and theta 2. On the other hand, look at this one. Again, I don't care about reflected. So here's the incident. So now we're calling the water n1, right? We're calling these angles theta 1. But the outgoing is the air, which is now n2 with theta 2. So you got to this is just one of these little picky things you got to remember, right? Incident, subscript 1. Outgoing, subscript 2. Incident, subscript 1. Outgoing, subscript 2. You got to remember that. We're going to be in big trouble. All right. Yeah, all right. I made a big deal about that. Okay, so that's nice. Now, Snell's law is responsible for the difference in the actual and actual and apparent depth of an object underwater. So here's what I'm talking about. So here's a fish. Can you barely see that fish? All right, so you know the light is coming in and reflecting off the fish. So let's just look at some of these light rays. So this light ray, you know, goes straight, then it bends away from the normal. This one, straight, bends away from the normal. Straight, bends away from the normal. Oh, I'm sorry, forget that. I was completely wrong. Let's back up. Here's the fish. Golly, here's the fish. So the light ray goes straight, bends away from the normal. Fish, light ray, bends away from the normal. Just goes straight, light ray, bends away from the normal, light ray, bends away from the normal. Now remember, you form the image from the outgoing rays, right? The outgoing rays are from which you form the image. So let's, here's an outgoing ray. These are all outgoing rays, right? So what you do is you backtrack. So that one goes there. That one intersects there. This one intersects there. This one intersects there. This one intersects there. Now this is out of scale and everything. Don't worry about that. So where does the kingfisher, the belted kingfisher bird, actually think the fish is? Well, all the outgoing rays intersect here, right? So the bird who wants to eat the fish thinks that the fish is actually here when it's actually there, right? So we call this the real depth of the fish, and this is the apparent depth of the fish. And again, that's just a result from Snell's law, the law of refraction. That's all there is. So, think about it. This fish, this bird, if the bird thinks that the fish is actually there, right? But it's not. It's really there. So I don't know how birds figure it out, but maybe they just keep going until they get the fish. I don't know. But anyway, it's kind of interesting, don't you think? So, like if you were in a boat and you were off to this, if you were off to the boat, if you were in a boat and you shot something down and you had it calibrated to only go this far, you'd miss every single time because the fish is actually lower or deeper. Okay, so apparent depth and real depth. Okay, this is kind of the same thing, but now we're looking from the side, okay? So let's say this is it could be like a fish bowl or something like that, right? So here's a glass container. This is all full of water. This is air. We're going to call this thing the optical axis. For this one, we could call this one the optical axis. There's no refraction. Okay, so here's the optical axis. So here's the real object. So again, the outgoing ray bends away from the normal because it's going from water to air. Outgoing ray bends away from the normal because it's going from water to air. And then if you're over here, you form your image by backtracking on the outgoing rays. So here's outgoing ray. Here's outgoing ray. So somebody out here would say that the object is there, right? Because that's where the image is. Okay? So again, this is the image, right? You just, like I say, you backtrack the outgoing rays to find the image. That's important, okay? You backtrack on the outgoing rays to find the image. So here's the image, but it's virtual because this is really not light, right? These dotted lines are not light. That's why it's called a virtual image. Okay, so the rays diverge from the virtual image at this point, right? Okay. And of course, there's a formula, all right? So this here, this is called the image distance, S prime. We're always going to do that, by the way. S prime is always going to be the image distance. S is going to be the object distance. So here, look, this distance here, the S, that's the object distance. That's the distance from the object to the boundary. The image distance is this distance, right? Or this here, S prime. And here's a formula. Ta-da! So there you go. S prime equals S n2 over n1. I mean, it's simple. The only way people get confused are they forget which is the n1 and the n2. So again, this is the incoming, this is the outgoing, so this is the n1, that's the n2. You just got to keep it straight. That's all. But also just use your head, right? Just draw the picture, and you know that S prime has to be smaller than S. So you should be able to figure out which is which. All right. Okay. You are underwater looking at a bird flying above. You see the bird where? So draw a picture, kind of like this or like this, But now, again, you're underwater now. You're looking at the bird. So pause your video and draw the picture. Okay. Okay, make sure you do it. Okay, make sure you do it. Don't just continue on and watch my answer, you know. Okay, the answer is a greater distance, and it really is. So I'm not much of an artist, but here. So here's the water, right? So there's water, here's air, and let's say here's the bird, all right? And, you know, so the light is coming from the bird. Now, we're going from small n to large n. So the rays, they bend toward the normal. Whatever. Okay? All right? So, you know, so you're seeing this ray, right? You're seeing this ray, and this ray, and this ray. And where do they intersect? Oh boy, I didn't do a good job. So where do they intersect? You know, they intersect way up there somewhere, right? Right. So you'll see the bird way up there, much higher than it really is. So make sure you understand that. Okay. Ah, I forgot to bring a mug. All right. Sorry, I didn't bring this. So this is something you can do at home, and it's fun. So you should really, really do this. All right. So place a coin at the far edge of the bottom of the empty mug. Hold on a second. Okay. So take a mug, put a coin on the bottom. Sit in a position so that you are just unable to see the coin. So here's the mug. Okay, here's table, mug, whatever, right? Here's the coin. And so it's an empty mug, right? So that's the light ray, okay? And so you can't, you know, here's the light rays. You can't see it, all right? So let's say that your eye is here or something like that. All right? So obviously, there's no water in here. It's just air. These light rays are not reaching your eye. So, all right. So place a coin at the far edge of the bottom of the mug, empty mug. Sit in a position so you're unable to see the coin. Then, without moving your head, utter the magic word, refraction, as you pour water carefully into the mug, right? On the near side, whatever. Okay. Pour slowly. Yeah, you got to pour slowly because you don't want to move the coin, right? So pour slowly so the coin does not move. The coin becomes visible when the mug is filled with water, right? So here, you know, it's not filled with water. You can't see the coin. Here it's filled with water. I don't know if you can see that. And you can see the coin. What's going on? Refraction, right? Because when you go from large n to small n, the water is bent. The light ray is bent. So there you go. So you should try this at home. It's kind of cool. Refraction, you know. Show your kids or something or your friends a magic trick. All right. Okay. Next topic. A lot of topics in this chapter. So total internal reflection. So you may have heard of fiber optics. So this has to do with fiber optics. All right. So here we have a light source in some medium. All right. So this is N1, again, with our convention, right? Because the incoming is N1, outgoing is N2. All right. And N1 is greater than N2. So this could be like a fiber optic, right? And this is air. And so let's look. So here, you know, it's 90 degrees, so there's no refraction, right? No reflection. Okay, here, most of it is refracted. And again, it bends away from the normal. And some is reflected, but most of it is refracted. Then we look at this guy. Now less, you know, so some is still refracted, not as much as here, though, right? And more is reflected. And again, the angle, it bends away from the normal. Now when you look at this light ray, what do you notice? So here's a refracted light, okay? So it doesn't escape. basically, right? If this is a fiber optic, this just doesn't escape anymore. So hardly any is refracted, most is reflected. Then if we make this angle even more, you know, there's nothing that's refracted, it's all reflected. So if you want to use this as a fiber optic, that means you set it up so the angle, so this is the critical angle, right? If the angle is greater than the critical angle, nothing is going to leave the fiber optic. So that's why it's called total internal reflection, because you just set it up so your angles are always greater than the critical angle, and then the light just goes, you know, it just keeps bouncing back and forth. And so that's how they do it, right? So when they're looking inside your lung, you know, with a fiber optic cable, and, you know, they can put some light down there, and they don't lose any of the light. So this is used in medicine, it's used in communications, and who knows what else. All right? So a couple things. As the angle of incidence gets larger, the transmission, or the refracted ray, gets weaker, right? Here's a lot, less, 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 nothing. Reflection gets stronger. The critical angle, okay, so this is theta 2, right? This is theta 2, the angle between the normal and the ray, normal and the ray. So here, theta 2 is 90 degrees. So the critical angle occurs when theta 2 is 90 degrees. And then total internal reflection occurs when theta 1 is greater than that critical angle. Okay, so let's do it. Let's use Snell's law to get an equation for this. I mean, you know, if you're going to work with a fiber optic, you've got to figure out what the critical angle is. So it's easy. So N1 sine theta 1 equals N2 sine theta 2. That's Snell's law. Now, we want to figure out the critical angle, okay? So we're going to say, we're going to put this to, all right? So all we're concerned with now is this, right? We want to figure out the critical angle. So our theta 1 is the critical angle. So I say N1 sine theta critical equals N2 sine theta 2. Now, what is theta 2 when theta 1 is theta critical? Well, when theta 1 is theta critical, theta 2 is 90, right? Critical angle when theta 2 equals 90. So I'm just going to say at theta, when theta 1 equals theta critical, so C, then theta 2 equals 90 degrees. So put in a 90 here. Now, what's the sine of 90? 1! That's nice. So that's just 1. So therefore, sine theta critical equals N2 over N1. There you go. I mean, that's all there is to it. All right? Oh, sorry. So that's really all there is to it. Okay? All right. And look, this has to be less than 1, agree? Because sine goes between -1 and +1. And so this has to be less than 1. All right? So, you know, for example, air is 1, water is 1.33. So all I'm saying is you're never going to get this mixed up. Because, if this is greater than 1, you know you're wrong because sine doesn't get larger than 1. So you're not going to make mistakes here, so don't worry about it. Okay, so again, that's used a lot in the real world today, so you want to be aware of it. Okay, next topic. So here, this is a prism, glass prism, solid glass prism. And you shine white light, like sunlight or something like that, through it. And what do you notice? You get this rainbow. And you all know this. I mean, some people have these prisms hanging from their houses or windows or porches or something like that because it makes this beautiful rainbow, you know. So what's the deal? You know, it looks like so in other words, the degree of bending depends on the color, right? Some colors are bent a lot. Some colors are not bent. Now, what's color? It's wavelength. So all this just says, you know how we always, you know, we've been talking about this index of refraction, right? And we've kind of assumed it was a constant all along. Well, it's not, all right? It depends on the wavelength of light. And you see this right here. So that's what's meant by the word dispersion. It just means that there's a slight variation of n with the wavelength. That's all it means. So here. So here's the wavelength, and here's n. So you can see for something called crown glass, you know, n is not constant, right? It's not a straight line. It varies with wavelength. Or flint, it varies with wavelength. So again, so that's just what we mean by dispersion. All right, this is a good place to stop.